All right, let's talk about a topic that makes a lot of even experienced Java developers sweat in an interview: concurrency. But don't worry, by the time we're done here, you're going to be ready to handle it.
So picture this. You're in the interview, things are going well, and then the interviewer leans in and says, "So, let's talk about threads." Your heart might do a little backflip, right? Well, after we go through this, you'll have the confidence and, more importantly, the answers for whatever they throw at you.
So here's our game plan. Think of it as our training regimen. We're going to start with the absolute basics, the building blocks. Then we'll get into the main reason concurrency is so tricky, synchronization. After that, we'll tool up with the modern stuff. And finally, we'll take on the final boss, a classic problem that ties everything together.
Okay, let's get right into it. To even begin to talk about concurrency, you have to have a rock-solid understanding of its most fundamental unit, the thing that makes it all happen, the thread itself.
You know, one of the first things an interviewer might ask is if you really get the difference between a process and a thread. And here's the absolute key. It's all about the memory. A process is its own little island with its own private memory space. But threads, they're different. They all live together and share the same heap memory. That's what makes them so fast and lightweight, but it's also the source of, well, all our problems.
So how do we actually bring a thread to life? Well, there are two main ways, but one is definitely the one you want to talk about in an interview. You can extend the thread class. It's straightforward, but it's also a trap because Java only lets you extend one class, so you've used up your one shot. The much better, more flexible way is to implement the Runnable interface. It keeps your tasks separate from the runner, which is just better design. That's the answer that shows you know your stuff.
You know, a thread's life is more than just on and off. It actually goes through this whole journey of different states. It starts out as new, just an object waiting to be born. When you call start, it becomes runnable. It's in the queue, ready to go. Once the CPU scheduler picks it, it's officially running. From there, it might get blocked trying to get a lock or go into a waiting state for another thread to give it a signal. And finally, once its work is done, it becomes terminated. Knowing this flow is absolutely key.
Okay, now for a question that I can almost promise you is going to come up. What is the difference between sleep and wait? This is huge. They both make a thread pause, sure, but they do it in fundamentally different ways. When a thread calls sleep, it holds on to any locks it has. It's like falling asleep in a doorway. Nobody else can get through. But wait is totally different. It releases the lock. It's designed specifically so that another thread can come in and change something. If you remember one thing, remember that distinction.
So, we have these awesome fast threads, and they're all sharing memory. What could possibly go wrong? Well, it turns out a lot. Let's talk about the central challenge of concurrency and how we protect ourselves.
And this right here is the #1 enemy, the race condition. It's exactly what it sounds like. You have two or more threads racing to read and write to the same piece of data. Imagine a simple counter. If two threads try to increment it at the exact same moment, you might end up with the counter increasing by 1 instead of 2. The final result is basically a lottery, and your data gets corrupted. It's a huge bug.
So how do we fight back? Our main weapon is the synchronized keyword. It acts like a bouncer at a club, making sure only one thread can get into a specific piece of code at a time. This prevents the race. Now here's the pro tip that interviewers love. Don't be lazy and just synchronize a whole giant method. Keep this synchronized part, what we call the critical section, as small and tight as you possibly can. It makes a huge difference for performance.
There's another important keyword to know, and that's volatile. Now, this is different from synchronized. It doesn't provide locking. Instead, it solves a visibility problem. It's a guarantee that if one thread changes a volatile variable, all other threads will see that change immediately. They won't see some old cached value. Just remember, it guarantees visibility, but it does not guarantee atomicity. It won't protect an operation like an increment all by itself.
Okay, knowing the basics like synchronized and volatile is crucial, but to really impress, you have to show that you're up to date with the modern, high-level tools. Let's get into the java.util.concurrent package. This is where the magic happens.
Seriously, in modern Java applications, you almost never create and start threads manually anymore. Instead, you use an executor service. And why is that? Well, it's a total game changer. It separates the what from the how, the task you want to run from the actual thread that runs it. More importantly, it manages a pool of threads for you so you don't accidentally spin up 1,000 threads and crash the whole system. It's the professional way to handle threads. So when you're giving tasks to that executor service, you'll usually use one of two things, a runnable or a callable. The difference is pretty simple. A runnable is kind of a fire and forget deal. You tell it to run, and you don't expect anything back. A callable, on the other hand, is for when you need an answer. It returns something called a future, which is basically a placeholder for a result that will show up later.
Ah, this slide is perfect. It really tells the story of how Java's concurrency tools have evolved. In the old days, you had hash table or synchronized map. They worked, but they were clumsy. They'd lock the entire map every time you wanted to do anything. Performance was terrible. Then came concurrent hash table. It is so much smarter. Instead of one giant lock, it has lots of little locks for different sections of the map. This means multiple threads can work on it at the same time, and performance is just way, way better. It is always the right answer in an interview today.
So what if all you need to do is something simple, like safely increment a number? Using a synchronized block for that is like using a sledgehammer to crack a nut. It's overkill. And that's where atomic variables like atomic integer come in. They use this really clever lock-free technique called compare and swap, or CAS. It basically lets you tell the hardware, hey, try to update this value to 5, but only if it's currently 4. It's incredibly fast because it avoids locking altogether.
All right, we've learned the moves, we've got our gear. It's time. Time for the final boss. This is a classic problem that interviewers absolutely love because it tests everything: threads, synchronization, waiting, notifying. Let's conquer the producer-consumer pattern.
Now here's the thing. A decent candidate might be able to code up one solution, but a great candidate can show them two different ways to do it: the classic, low-level way and the sleek, modern way. Showing this proves you don't just memorize patterns, you actually understand the principles underneath.
First up, the classic approach using wait and notify. This is where you're doing all the hard work yourself. You have a shared buffer, you wrap everything in a synchronized block, and you manually check the state. If the buffer's full, the producer has to wait. If it's empty, the consumer has to wait. Then you have to remember to call notify all to wake everybody up. It's powerful, but it's also incredibly easy to make a mistake.
But now, look at this. This is the modern way, using a blocking queue. It almost feels like cheating. It's so simple. The producer just calls put. If the queue is full, the method blocks automatically. The consumer just calls take. If the queue is empty, it blocks automatically. All of that complicated, error-prone wait and notify logic, it's gone. It's all handled for you safely inside the queue. It's cleaner, safer, and just better.
So why does knowing both matter so much? Because it tells a story. It proves you understand the low-level mechanics, the nuts and bolts of how wait and notify work. But it also proves you know when to reach for the powerful, modern tools that make your life easier and your code safer. You understand the history, and you know how to use the best tool for the job today.
And there you have it. The building blocks, the core challenges, the modern weapons, and the final boss battle. You've got the blueprint now. You're ready for that interview. So the only question left is, what amazing things are you going to build with this? Go get 'em.